Alright, so before I start this one, I gotta make a mistake in this part. It will actually just be 100 because this part here with the equation is actually just the k's will cancel either way. So you just end up with this not being here anymore. I mean, the conversion correct, but the conversion wasn't needed. So this will just end up being 100. So my original answer was correct. Yeah, I think majority of you all noticed that in the last one. So it'll be 0.836. Yeah, because the K's were cancelled. Because I base is KVA and root through KVB. So VB is 69K. This was 100,000. So the 1,000 will cancel with the 1,000 to get 100. And yeah, I get that. Cool. Alright, so in this video, we going through faults really. So in the exam, they will tell you what bus the fault happens on, and they will tell you the type of fault that happens on the bus. So for this video, the type of fault that happens will be a three-phase fault, three-phase balance fault, meaning all three phases go into ground. So you have different types of faults. Faults in itself is a topic, but for now we focus on the reduction of the circuit. So after you get the circuit in its per unit form, in this case, I said the fault was down here. So basically, if we were to draw it, since it have no impedance between here and here, the fault basically will be seen in this bus. So basically, the fault happened here. So what we have to do now is draw over an equivalent circuit to look like this. So you have here Z per unit equivalent to your faulted bus, to your fault, and a generator. One angle 0, of course. So we look at the circuit itself and try to see if we could really saw where to start. So all these transformers here, they are all in parallel, right? So because all the transformers at the end go to ground, so they're all in parallel. So because they're in parallel, two transformers or two impedances in parallel at the same impedance that is will just be divided by 2. So I'll just use this page. So you basically just get one generator there, and it was 0.0133 divided by 2, and end up with 6.65. No, that's 6.5. Let me try that again. 0.0133 divided by 2. Yeah. So here will be 6.65 by 10 to the minus 3. And the other side was the same too. And both of those connected to bus. So what else we could use? So these two impedances here, they are in series with each other. So you can add them together and just create one series stuff. If it had an impedance in between here, for some reason, these two wouldn't be in series anymore. Right? So because it's not, there's two series lines, you could just find the equivalent impedance. So here will be 0.089 divided by 2. So get one impedance. and then the bottom one will be 0.0499 divided by 2. Because 0.02495. Then you have your bus and any faults. So if we continue to reduce it, these two generators on top here, we could do our next product over sum to get one impedance. So it'll be 6.65 divided by 2. Then these two here in parallel, well, in series, sorry, be 0.0445 plus 0.02495. We get 0.06945. And then these two in series. So it'll be G, 1 angle 0, and you add those two, plus 3.325 10 to the minus 3. So we get 0.072775 G bus fault. And this will be the equivalence. Yeah. So that's how you do those. That's how you convert it and reduce it. So these two in series, because it had no impedance in between, and all these four in parallel technically. And they just keep reducing until they get one impedance generator, bus, and a fault. So this will be the equivalent. And with that, the next thing I will ask you to get is something called a short circuit current or a fault current. And I short circuit will be 1 on Z per unit. So in this case, it will be 1 on 0.072775G. According to how much decimal places used, I'm gonna just put my calculator in complex mode. 1 divided by 0.0727775G. So, yeah. So, it basically end up, I'm gonna switch my calculator back to give him my answer in complex form. So it'll be negative 13.74G. And this is per unit. Cool. And the next one is your MVA short circuit per unit, which is basically a V per unit multiplied by I short circuit per unit, and V per unit is 1. So in this case, your MVA short circuit is your I short circuit. This is always 1, at least for this course. So your MVA short circuit per unit will be a I short circuit. So therefore, this is negative 13.74 J MVA. This will be amps. And then now if you want the actual, because this per unit, if you wanted the actual ones, so to get the actual, you just multiply it by the base. So I actual is just equal to I short circuit per unit multiplied by the I base. So I short circuit that was negative 13.74 and the I base was 0.836, and you'll end up with 11.5. You see, so this was yeah, I think this was let me see, 1 divided by 0.0727775. Yeah, pretty many. Anyway, yeah. So we get 11.5 amps, negative 11.5 amps, and then here MV actual equal to MV short circuit per unit by MV base. So it'll be 13.74 negative multiplied by 100 to end up at negative 1374.5 GMV. And basically that's how the computer scrambled for these questions. So how the question will come is they will give you one of these circuits. They will tell you to reduce it to its equivalent form, which is basically this. So we had to do all the conversions to MVA base. They'll give you MVA base and a V base. Then they will tell you where the fault is, and you just have to redraw the circuit to get it to its equivalent form. And then after that, you have to calculate your short circuit current, and then your MVA short circuit, and then the actual for both of them. And that's where it will end. Alright, any mathematical mistakes, I apologize, but I mean, as the steps are important, obviously, when you actually do it with the equations, you may get different answers, but I mean, that is all in the process. But the steps are the same. Alright, so I'll put my solution in the description so you can check it. And if I make any mistake, I will tell me. I'll just edit it. But that is it. That is it. So check in the next one. So the next one I'll be going through the different types of faults and that what you gotta do in ISIS. And we'll talk.